Today's lesson. Today we will be looking at some various air sampling and measurement methods and equipment. So these are the objectives we would be expecting to fulfill at the end of today's lesson. So at the end of today's lesson you should be able to describe the types of air sampling devices that would be used for collecting air samples, be able to perform gas sampling procedures, perform particulate sampling, I beg your pardon, there's a typographic error there, and also be able to discuss smoke and soiling measurements and stack sampling. So we begin today's lesson by just recapping a few meteorological issues that we need to be reminded of, because what goes on in our atmosphere also helps to contribute to some of our air pollution concerns, and also we have to be reminded that the way in which our air currents move, this also aids in the transportation of air pollution. So what we have on this diagram is we have several global weather systems all occurring at the same time. So if you look, we see some of these weather systems, they occur at various latitudes. So around our equator region we have Hadley cells. As we move further north and south of the equator, we have what we call Ferrel cells, and then closer to the poles we have polar cells, I beg your pardon. So if you look carefully, you can see that what we have is a pattern of warm air rising, cool air sinking. So we have a cycle going on at in each of those weather systems. But note that they are not all moving in the same direction. If you look at what's happening at the equator, we see that the winds move in opposite directions, north and south of the equator. And similarly, if you compare the Ferrel cells north and south as well as the polar cells north and south, you see they move opposite to each other. Now what happens is these weather systems, they are observed over many years, and these observations and the patterns that are observed over long periods of time, this is what will determine global circulation patterns. It's important, please note at the bottom here, the Hadley cells have the most regular pattern of air movement, right? So in other words, they're fairly predictable, and they also produce the most extreme weather at the equator. So we're talking about in this area here. So right, and the reason for the differences in the circulation patterns north and south of the equator is what we call our Coriolis effect. And the Coriolis effect is the spin of the earth, the way the earth spins on its axis, that induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. So move on. So what we are looking at here is we're going to be looking very briefly at how the movement of heat and the way in which heat behaves in the troposphere. Alright, so if you recall, we looked at the different atmospheric layers, and the troposphere is the one that occurs closest to the earth. Right, so some of what we would be interested in, for example, is the greenhouse effect. What is the greenhouse effect? So the greenhouse effect is a process by which radiation from a planet's atmosphere, in this case the radiation source would be our sun, how it warms the Earth's surface to a temperature that is above what it would be without its atmosphere, right? So let's see what's happening. So we have radiation or heat energy coming from the sun, and it enters the Earth's atmosphere in various ways. We have some where 20% is scattered by clouds, 86% by the atmosphere itself, 19% absorbed by the atmosphere and clouds here as well. We have some directly absorbed by the Earth's surface and some by reflection. So these are the number of ways in which heat would enter the Earth's atmosphere and it would warm up our atmosphere. So if you recall, typically what's happening is we have several things happening in our atmosphere. We have apparent holes in our ozone layer. Remember, our ozone layer is that protective layer that filters out most of the dangerous solar energy coming into the Earth's atmosphere to help keep our atmosphere, that's the troposphere layer, to help keep it in balance in terms of what life requires. Okay, here you can see once the heat enters the Earth's atmosphere, some of the ways in which it would behave. So again, we know the Earth would be heated by conduction, right, directly from the sun. When the Earth is heated, it would be released from the Earth as convection heat, and then we have, and this is what often causes the development of our weather systems. Here we also have the Earth being heated as well from the atmosphere itself, not only directly from the sun. So we have some atmospheric heating taking place here, and these types of patterns of heating is what contributes to our weather systems. For example, everyone should be familiar with the water cycle. So we know that the sun heats up the atmosphere, causes water vapor to turn into droplets. It would fall as various forms of precipitation, not only rain, infiltrates our soil. We'll have runoff, so we have contributing to groundwater as well as surface water, and then again the cycle continues indefinitely. Alright, so these are some of the heating systems that occur in our atmosphere that contribute to our weather systems, and as we continue to discuss, we will understand how these weather systems, what role they play in air quality. So let's look at the influence of meteorological phenomena on our air quality. So in other words, the weather. So most of us by now should be familiar with the term lapse rate. So what is lapse rate? Lapse rate is defined here for you. This is the rate of change in the atmospheric temperature that is observed while moving upward through the Earth's atmosphere. Alright, so typically what happens is the air would be warmer in the lower levels of the atmosphere. As the air rises, as that warm air rises, it begins to cool as it rises further into the atmosphere. Alright, so we need to remember that, keep that in the back of your mind. Secondly, we have to be interested and concerned in pressure systems. What pressure systems occur in the Earth's atmosphere? So typically where you have high pressure, this is a primary weather system responsible for conditions that lead to poor air quality. Alright, so with regards to pressure and temperature, typically there is a direct pattern, a linear pattern of increase where your temperature increases, your pressure increases, right? So what you would need to remember is typically associated with high temperature and high pressure, this contributes to certain atmospheric chemical reactions taking place. So if you recall, in previous lessons we talked about these chemical reactions that can take place in the Earth's atmosphere, that can actually contribute to the development of acid rain. So here we have to be very concerned where we have pollutants being released into the Earth's atmosphere. What kind of temperatures and pressures do we have, because it can actually encourage the development or the increase in poor air quality. Also, where you have temperature inversions, So a temperature inversion, this occurs where you would have a layer of cooler air that is trapped near the ground, and above that you would have a layer of warm air. So it's called an inversion because remember, this is not normal. Normally what happens is as the air rises, it cools, so cooler temperatures should be in the higher levels of the atmosphere. So where you find an anomaly with colder layers beneath a warmer layer, this is what we call our inversions. And where this occurs, this actually traps pollutants near the Earth's surface and allows it to accumulate. And remember, this is where most of life occurs, in the lower levels of the atmosphere, in your troposphere. Additionally, we have to be concerned about winds, because winds would be responsible for the transportation of our pollutants. So for example, if the source of your pollution is upwind of your of the winds, all right, this now allows the wind to blow by the source of the pollutant and transport those pollutants into other areas. So this is a very serious concern where air quality is concerned and where air pollution is concerned, because many times everybody needs to be concerned about air pollution, because we may not be perpetrators of the air pollution, but we can be affected by it. Also, winds can be responsible for the recirculation of pollutants. That is when the winds can pick up more pollutants from other areas and then return to the location, increasing the accumulation of pollutants in the atmosphere. So the wind not only transports it, but it can actually pick up more and bring it back towards you. So we need to be concerned about that as well. Additionally, moisture or humidity in the atmosphere. Where we have low humidity, we will have an increase in the buildup of air pollution. Alright, pollution will build up where there's low humidity. Where you have high humidity, you will have increased absorption of particles, but it also leads to poor visibility. So essentially what happens is, when the air is dry, it does not move as much, and because it's not moving, it allows the pollutants to build up, right? For example, on days when the ozone is high, the relative humidity is often low, okay? But where you have increased humidity or increased water in the atmosphere, as mentioned, it absorbs the particles, causing them to swell, and as a result, it reduces visibility, makes it very difficult to see. Alright, so here, these are some of the reasons why we would need to be concerned with what kind of levels of humidity we have in our atmosphere. So here, this schematic just gives you an idea of the various components involved in the transportation of pollutants. So here we have our source of our pollution. Imagine this is an industrial plant. We have the recipient, which is you. Okay, now if you have wind blowing, as I said, wind can blow in either direction. So if you have wind, the source upwind of the plant, the wind would be blowing from our left to our right, and as a result, it will transport the pollutants towards the recipient. Similarly, it can work the other way. It can blow from the right to the left and transport the pollutants into other areas. Now, with regards to wind speed contributes to how quickly the pollutants are carried away from their original source. So when you have a very windy day, you can expect that air pollutants would be transported further and more frequently from the source of origin. So this is how wind speed contributes to air pollution. Now let's look at how temperature, some details as to how temperature changes with elevation. Alright, so we have our graph here, y-axis elevation, x-axis temperature. Right, so I have some definitions right here on the screen for you. So the adiabatic temperature changes. So as the air is heated, it expands, becoming less dense, and as a result lighter. Okay, because it is lighter, so we're looking at the increase here as the temperatures, as you go higher into the atmosphere, the temperatures begin to decrease, right? So as it is lighter, it rises upward above the cooler air, right? As it does so, the air continues to expand. This is because it has less pressure in the atmosphere, allowing the air molecules to spread out. So basically what we're saying is, this is the normal conditions. Adiabatic represent normal conditions. But then we have conditions that would be out of the ordinary. For example, super adiabatic, that would be representing this line here. Super adiabatic, this is unstable, right? So it falls in this category of unstable atmosphere. So this is where the temperature decreases are greater than 10 degrees per 1,000 meters. So in other words, the temperature is cooling at a faster rate than adiabatic. That is what is happening, and this often occurs on sunny days, and these conditions are actually excellent for the dispersion of pollutants in the atmosphere. All right, so it's unstable, but it's good for dispersion. Subadiabatic, which would be this one, this is considered stable conditions. So the atmosphere is stable. It's characterized by little temperature changes with height. So notice how steep this angle is, and if you look at the difference between this point and this point, you notice that the temperature change is minimal. Okay, this dispersion conditions here are moderate. All right, so it's actually for super adiabatic, best dispersion conditions, subadiabatic, just moderate dispersion conditions. And of course, if you recall, adiabatic represents what is normal. Okay, so again here, this just represents how the pollutants would be dispersed according to the atmospheric conditions. So if you recall, super adiabatic, if we look again, super adiabatic is unstable conditions. Your pollutants are being released from the source here. Notice your dispersion of pollutants is basically unstable, and some of it is being released close to the ground. All right, during unstable conditions, the pattern is described as looping. If we continue here with adiabatic is normal. Dispersion would look like this. All right, it's not too close to the ground, but it's not great either. This is normal condition. So this is coning. This is what the release from a stack would look like. Okay, similarly, if you have an inversion, and if you recall, an inversion, that is where you have a layer of cooler air closer to the surface overlain by a layer of warmer air, and if you look at how it disperses, the pollutants are dispersed, it remains in the lower atmosphere. It's not able to rise because it's being blocked by that area of warmer air. Okay, and this is called a fanning plume. These charts here just represents what we had been looking at in the previous slides. Now this is where you have a combination of inversion and super adiabatic. So super adiabatic, again, unstable atmospheric conditions, and then you also have an inversion overlaying that. So that's what we're looking at here. So you have the unstable conditions below, and then overlaying that you have an inversion. So you have an unexpectedly colder layer of air, on top of which you have a warmer layer of air, and we know that makes it difficult for dispersion. So this is what dispersion would look like. You find it again, it would be staying close to the ground, and then it flattens out like this because it's unable to rise normally. Alright, so this type of pattern and dispersion is called fumigation. We talked about looping, so this is another example of looping. Again, we have at the lower temperatures we have stable conditions. As temperatures increase in this direction and in this elevation direction, we have an inversion. So that's a colder layer of air blocking the dispersion of the pollutants. Okay, and this is what causes looping. So if you essentially looping would be associated with unstable conditions. Okay, so as we continue, we would look briefly now at air quality management activities. So what do we do? What methods can be used to achieve the management of the quality of the air around us? For example, monitoring would be very important. Monitoring can be achieved through the use of national ambient air quality standards, ambient being environmental, right? So if you have standards in place by an authority that has, by an agency that has the authority to monitor, implement and enforce these standards, you can encourage compliance to these standards. Okay, so it's essential to have standards in place because it facilitates monitoring for the purpose of enforcement of those standards. Additionally, providing the public with information regarding ambient air quality levels. So it's important for that information to be provided for the public. For example, low air quality on a particular day can alert the public to take precautions when necessary, that where it can affect health of the general public. You can also look at measuring trends in the air quality, because this will require data collection, and where data is available over a long period of time, it's possible for you to identify trends, whether air quality seems to be declining over time. That would be an alert for the authorities to know that they would need to put measures, policies, laws in place in order to try to stem the direction of those trends, and if at all possible to reverse it. It's also important to establish relationships between the exposure to the pollutants and the health effects, to inform regulatory decisions. So this is basically saying this is where researchers and scientists and health professionals will get involved, because when data is provided from all these different sources, it is very possible that you can establish that if certain amounts of pollution is released into the atmosphere, or certain types of pollution is released into the atmosphere, that they can be associated with certain health effects. If this is established, government and authorities now can use that data as a basis for establishing laws and regulations to improve the situation. Additionally, developing and evaluating your air quality in terms of using modeling tools. Now, what are these modeling tools? These modeling tools are actually techniques that would be used to simulate physical and chemical processes that affect air pollutants. Alright, so these are tools that the scientists would use in order to identify trends, or to simulate results or outcome based on changes in the environment that they may expect to happen. All right, so these are all tools that can be used to help manage air quality. Okay, so what are some air quality management issues? Right, so continuous measurements of particulate matter, PM, include measuring the mass and the components of the particulate matter that is released into the air. So this is important. This kind of information is needed in order to facilitate any kind of control measures. Okay, it's also important as well to for your dry deposition measurements for mercury, to gather that kind of data, right? Dry deposition measurements of mercury. Why mercury? For example, if you have mercury emissions, so your mercury emissions can be released into the atmosphere in various forms, gaseous form, particulate form, and the amounts of this released into the atmosphere will affect the ecosystem as well as human health. Okay, so we need to know, we need to be able to quantify these amounts and in the various forms. When it gets into the ecosystem, for example, it can enter our watersheds, affect our various sources of water, get into our food chain. Then you will have bioaccumulation taking place, and everything feeds back to human health at the end of the day. Similarly, you would need to be able to measure for lead in your particulate matter as well. Alright, we know that lead is an environmental toxin that affects virtually every system in the human body. It can lead to brain damage or even death. Alright, some major sources of lead would be gasoline, etc. We know lead poisoning, as I mentioned, affects the nervous system, and it's particularly damaging to vulnerable groups such as fetuses and young children as well. So all of these types of pollutants, it's so important for us to be able to determine quantities that have been released into the environment. Also, the measurement of air pollutants that contribute to the formation of other pollutants. For example, what is ammonia's role in the formation of nitrate and sulfate particles? So we would want to know that. For example, ammonia is widely present in the atmosphere due to human activities as well as natural sources. So some human activities would be from agriculture, industrial and motor vehicle emissions. Okay, and when these particulates are released into the atmosphere, they form ammonia salts such as ammonium sulfate and ammonium nitrates. Okay, so again, this is another one that we need to be able to quantify. And these measurements of we also need to be able to measure the toxins in the air. Alright, so moving on. So we're going to talk now about how do we measure smoke and soiling, I beg your pardon. Alright, and we would look at these three methods of measurement very briefly. So the first one is the Ringelmann smoke chart. You should be familiar with this one. So we know the Ringelmann smoke chart. This gives shades of gray by which the density of columns of smoke rising from stacks can be compared. So this really is a visual measurement. Right? It was developed by Professor Maximilian Ringelmann in 1888, and it actually has 5 levels of density: 20, 40, 60 and 80%, and beyond that it's considered black. How does it work? The darkness of the visual comparison to the chart depends on the particulate size. So the size of the particles in the air, the concentration of it, how much is released into the air in that particular space, the depth of the smoke column being viewed, and also your natural lighting conditions. How good is the lighting? Because if you have darker, if you're taking your measurements during darker overcast periods, the lighting would be affected and it may look darker than it really should be. Alright, how do you use it? You stand at a distance from the stack. Make sure the direction of the stack, the wind speed and the wind direction allows you to actually properly view the information, visually view the information, because all of these things, wind speed, direction of the wind, the direction that you're standing from the stack, these can all affect your ability to view the data. Alright, this should also look familiar to you, those various densities that we were talking about, right, from 0 to 100. So there are actually 6 categories within which you can place your results. Okay, at this point I would like to ask you to proceed to part 2 of today's lesson.